Hi folks, I guess we are live. Let me just check the connection, and could you also please confirm on the chat window if you can see everything, if you can see my screen and hear my voice, because I'll be mostly doing screen share. Can you please confirm that? Hi folks, I guess. Yeah, I can hear myself back, so I'm assuming that there are no major hiccups whatsoever. So please confirm that, so that just let me know if you see any hiccups from your side. Okay, so this looks good. I can see the live feed itself here. No major problems that I encounter. Cool. So hey, good evening, folks. Good evening. So you can see the screen and you can hear me, right? You can see and listen. Okay. Okay, sounds good. Good. That's good. We'll start the session in about 10 minutes from now. As usual, I come a few minutes early just to ensure that there are no technical hiccups. So since we are a few minutes early, I can take a few questions and just let me know if there is any question that I can answer. Do let me know and I'll answer a few of these questions. Then we'll go into the basics of linear algebra session that we plan to do for the next 2 hours. So somebody says, what can be the strategy for data structures and algorithms for software engineer and machine learning roles? I think we have mentioned this in the past live sessions also. Okay, so for a software development engineer, especially if you're looking at top product-based companies, you should pick one of the major programming languages. It can be Java, C++, any object-oriented programming, Python. Again, Python is a very popular language now. But I see a lot of people doing Java also, fewer people doing C++. Again, data structures and algorithms, we have discussed a few of the basics in the previous live sessions, but you should be able to solve, given a problem involving dynamic programming or a good, interesting problem. The expectation at a top product-based company is that from the time the problem is explained to you, you come up with a decent solution and write code in any major programming language in 20 to 25 minutes. Okay, that's the expectation. So in a typical 1 hour interview, you will be given one easy, one medium. Again, depending on the performance, you might be asked a medium or a slightly harder question. That's it. Okay, so this is what is expected in a 1 hour interview. Again, for a fresher, you will not be asked lot of design. So if you are an experienced software engineer, you will be asked software design, like low-level design, high-level design. As you become senior and senior, there is more focus on architecture design or high-level design. If you are a youngster, not so much focus on design. For entry-level software development engineers, it is simple programming, data structures, algorithms. In some roles, they might ask SQL also. Okay, some questions on database, especially if you're a computer science student, they might ask questions on databases, operating systems, etc. But only 5% of the time they ask in databases and OS. Most of the time they'll ask on data structures, algorithms. For a machine learning engineer or a data scientist, the bar is lower. So the complexity of questions asked are certainly not at the software development engineer level, unless you're a CSC student or you come with prior software development experience. Right? So the bar is typically one level less than software development engineers. Typically, you will have 1 round or maximum 2 rounds of SDE-like interviews. Again, in these rounds also, there will be focus on the problems that are typically asked are simpler than a typical software development engineer. There is, of course, some focus on SQL for most data science roles because they expect you to be able to write SQL queries. The complexity of problems is certainly lower than software development engineers. Like most companies typically have 1 round. Again, this round also, the complexity of this round depends whether you come from computer science background or you come from non-CS backgrounds. If you have worked in software, if you worked as a software development engineer, certainly the bar is going to be like a CS student, right? So again, there will be, most of these questions are not hard, to be honest with you, right? So we have solved some problems in the previous public live sessions. They are a good benchmark. Again, I've picked up a few problems from my own interview experiences of others in top product-based companies and showed them in the previous live sessions, right? So you can check those out. Cool. Okay, somebody has another question. Sagar says right question, Vijay. Okay, which question is this? I heard we couldn't write better implementation of data structures using Python when compared to C++ and Java. Is that true? That's a good question. The biggest problem with Python is it is slow. Okay, this is one of the biggest problems with Python. So what happens is lot of data structures, lot of numerically intensive computation that we use in Python. For example, take a list, right, or take a dictionary in Python. All of them are internally implemented using C++, because that's where the speed comes from. Again, don't think that Python is not production quality. There are a lot of companies which use, like for example, take Google, right? Probably one of the best software engineering companies in the world that I know of, right? They write most of their production code in C++ or Python. Of course, they also write some in Java because Android is based on Java, right? But they use Python in production, right? Look at TensorFlow and Keras, right? Which are some of the most popular machine learning libraries. The reason everybody created Python interfaces for that, again, the core implementation itself is in C++ for speed. But Python is much more easier to run, easier to maintain, easier to pick up, and the breadth and depth of libraries that you have in Python are like, I don't think any other programming language today can even come close, especially for data science and machine learning applications. This is almost one of the best, hands down. Right? So don't think Python cannot be productionized. It can be productionized if you use the right data structures and right libraries. For example, there is a lot of Numpy code which is actually productionized because all the internals of Numpy, as we have seen in the previous live sessions, is implemented in C and C++. Right? All of the operations underlying Numpy are actually written in C++, making everything much, much faster. So Python, as long as the critical time-intensive stuff is implemented in C++, Python is more or less production ready, right? So again, if you go to an interview, if you say, okay, I'm a Python guy, I prefer writing code in Python, nobody will hold it against you. But you should know the limitations of Python, right? You should know where Python lacks, where Java is better, where C++ is better. That high level understanding is good enough. Nobody will hold it against you that you are using Python. Okay. Somebody says you want a class on deep learning using computer vision. Again, as I mentioned to you earlier, we are going in a sequential manner. We completed most of module 1, which is basics of Python programming. Today, today we are doing linear algebra. So I'm going step by step, chapter by chapter in our course videos. And certainly, hopefully, since the lockdown is also extended to May 3rd, we will be able to complete most of the chapters that we have in our course videos by the end of the lockdown. Right? So we are going step by step. Okay, that's important. There is no point me jumping directly to deep learning. We'll do that. Again, today we'll see a very simple, in linear algebra, how a lot of computer vision operations are actually simple linear algebra. Right? We'll see one of the examples in today's live session also. Cool. Okay, good question. Sandeepan. So what is the difference between basics of linear algebra and linear regression? I'll mention this. Again, we'll wait for a few minutes, let everybody join in, couple of minutes. It's 6:01. So I have a detailed notebook. I'll share this notebook by the end of it. I'll tell you what we will cover today, what are the future sessions in which we'll cover other topics. Okay, of course, linear algebra, if you look at a typical linear algebra textbook, it covers a lot of things. It covers even linear regression. Right, so we'll do that. Okay, so somebody says, okay, I've answered this question multiple times. How do the roles of data scientist, ML engineer going to change with auto ML? Again, the most important thing here is even if you are using auto ML architectures, look at any auto ML architecture in the world, right? Even the best of the best at Google, right? So auto ML speeds up the pipeline for you. Okay, I worked in a world where we did not have scikit-learn like libraries. Okay, in that world, we had to implement a logistic regression function. Okay, we had to, I also implemented simple multi-layer perceptron, simple convolution neural network again, this is before TensorFlow, before Keras days. So what happened in the world is these libraries made our life simpler. Okay, because I have scikit-learn, because I have TensorFlow or Keras, because I have XGBoost. Again, we have implemented GBDT at scale in my previous company, right? We implemented GBDT at production scale before we used XGBoost. So even before these libraries existed, the machine learning folks were implementing these things and using them internally within the companies. So what these libraries did was it speeded up the whole thing, right? So what it gave us is speed in terms of trying out new models. Again, without TensorFlow, Keras, and PyTorch today, building deep neural network models from scratch is fairly non-trivial. Okay, because we have TensorFlow, Keras, and PyTorch like libraries, we have simply improved it. AutoML, as we see it today, is mostly being used in the framework of deep learning for architecture search, right? So for the task of architecture search, right? So what is architecture search? For those of you who know a little bit of deep learning, suppose you train a deep learning. Again, there are a bunch of very popular deep learning architectures that you have, but if you want to search for the best architecture for your problem, it requires a lot of hyperparameter tuning, right? It requires a lot of hyperparameter tuning and a lot of experimentation. What AutoML is doing is it is simplifying and speeding up that process. See, look at what is the scope of AutoML today, right? Can AutoML design features automatically for you from tabular data, right? Can AutoML, given a real world problem, can AutoML pose the problem and solve it end to end? We are not yet there. We are actually far from it. Okay, just because, the analogy that I give here is, just because there is compilers doesn't necessarily mean that there are no software development engineers today. Compilers, what did modern compilers do? Right? Pre-compilers, people wrote software, but compilers made life easier. And it made programming accessible to many, many people. People who didn't know how code works internally, people who didn't know linkers, loaders, the system software, okay, how the operating system works. Now, somebody can write code in Python and not care about how things work internally. The compilers, interpreters, loaders, linkers, everything take care of it. So they made life easier, democratizing access to programming. But even with all of this, there is a huge demand for software development engineers. I think something very similar will happen, right? People who have core expertise in machine learning, AutoML, whether it is AutoML or whether it is libraries, right, like TensorFlow, they make our life simpler and faster. Okay, this also makes the whole technology accessible to a wider set of people. But that does not mean that the demand for machine learning engineers or data scientists decreases. Because of modern compilers and modern programming languages, the demand for software development engineers actually skyrocketed, right? So look at Python or look at Java. Because they're so beautiful languages where compiler takes care of so many things, there is more demand for software development engineers today. I think all of the libraries, all of the AutoML stuff today will increase the demand for machine learning and data science folks because more people can access it, more companies can build these technologies at a lower cost. Right, cool. So somebody says, is it necessary? Okay, it's already 6:06, so let's dive into it. I'll take these questions again after a while, right? So let's dive into the session itself. This is by, again, I'm writing this in Colab so that it's easier for me to share it with all of you. As I've mentioned in the previous sessions also, I will share this Colab notebook at the end of the session, right? So at the end of the session, I'll share this Colab notebook with all of you in the comment section itself, also in the description section of this video. So don't worry about it. So let me list down the scope of today's session. So this session is called Basics of Linear Algebra because it's impossible to cover a lot of concepts in linear algebra in just one session. That's why even in our course videos, we broke it up and taught various aspects of linear algebra at various points in the course, right? So I'm assuming that you've already gone through the link that I've mentioned in the, again, somebody is asking, can you send the video? Don't worry, you will get the video also. It will be on YouTube. Okay, so since this is a public live session, you can access it even after the live session is over. Okay, so I'm assuming in the announcement video, I gave you a link to free videos on our course. I hope everybody have gone through it because I'll not be repeating the mathematical concepts that are there, just in the interest of time. And the agenda today is to take the mathematics that we have already covered in the course videos and convert it to code. Again, all these will be simple concepts. Linear algebra is a beautiful topic with lots of areas, right? So what we'll limit ourselves to is only the linear algebra basics chapter in our course, right? There are lots of other concepts. For example, there are tons of operations like normalization, standardization, etc. that you do on data matrices. This is what we'll do in future sessions. There is a lot of matrix algebra like principal component analysis, singular value decomposition, non-negative matrix factorization. Again, we have covered these concepts at different points in our course. For example, in dimensionality reduction chapter, we covered PCA, right? So SVD and NMF we covered in the chapter of recommender systems, right? So there are tons of concepts. If you open a standard textbook like Gilbert-Strang's textbook, again, this is one of the best books. But again, remember that this book is written for applied mathematics students. This book is written keeping in mind two courses, two undergraduate level courses or two courses in general at MIT, right? So this is just two courses just of linear algebra. So my suggestion is, if you want to be in machine learning or if you want to be in machine learning, again, the problem here is if you start watching just Gilbert-Strang's videos and if you just start solving his problems, you'll become very good at linear algebra. But remember that linear algebra is just one of the many topics that you need to know to become good at machine learning and data science. So my suggestion to all of you is this: first, learn the basics which are needed in the context of machine learning and data science. Once you learn all of that, if time permits, go ahead and read Gilbert-Strang, right? So please don't do, again, a lot of people do this. They do depth first. They just go into linear algebra and they learn everything in linear algebra. This will take you 1 year. To be honest with you, to finish Gilbert-Strang's book comfortably, if you put in 1 or 2 hours every day, it will take you easily 1 hour to do it. Comfortably, if you do the assignments, if you do the code part, everything perfectly, right? So my suggestion here is, linear algebra is just one of the many aspects that you need for machine learning data science. So learn all of that. Later on, my suggestion always to anybody who's learning a concept is first to do breadth first. Learn all the concepts basic concepts that you need. Then for every concept, there is a depth. Go first, get the breadth so that you can start transitioning to machine learning data science jobs or data science roles. And then there is a whole lifetime to learn depth, right? I'm learning, again, if you think probability and statistics, right? I'm learning some causal inference based models even today. I mean, this is lifelong learning, right? So there is no end to it, okay? So instead of going depth first, I recommend you do breadth first. Okay, so what we'll do, again, that's also the philosophy that we have taken in our course videos. First, we explain the basics of linear algebra, and then we would go into each of these concepts later. Okay, so in future live sessions, we'll cover a lot of data matrix operations, principal, all the data, all the factorization methods. Again, lot of linear algebra also has linear regression. If you look at standard linear algebra book, you have linear regression. Again, this linear regression can be covered from linear algebra perspective, also from optimization perspective, right? So in our course, we cover it both from optimization and linear algebra perspective, and we'll cover it in the future sessions. There is also linear optimization, okay, which is related to linear concepts in linear algebra. We'll cover that in future sessions, right? So this session is going to be that's why I wrote basics of linear algebra. There are many other concepts that we'll cover in future sessions as per our course syllabus, okay? Cool. So second, very importantly, so this is the agenda that I have today. Okay, first we'll go to vectors and hyperplanes. We'll learn a little bit about matrices. We'll take a diversion and I'll explain you about the concept of convolution, because I wanted to show you applications of matrices to image processing and computer vision. Just one application, of course. We'll do one whole session on just one or more sessions on computer vision and image processing. I just wanted to do a simple example here. Then we'll do some basic hypersphere stuff. I'll also tell you other topics, and people who want to learn more undergraduate level linear algebra, we have some videos for that which are publicly available. I'll share that also. Okay, that's the whole agenda. So let's start here. Let's start with vectors and hyperplanes, right? So very simple. So imagine, again, I'll not be repeating the mathematics that we've already discussed in our course videos. Okay, just in the interest of time, please understand that. Okay, so let me represent this way. Pi 0 basically is a hyperplane that passes through origin. For a hyperplane that passes through origin, you just require the normal to the hyperplane. Okay, that's good enough to represent the hyperplane. I'll represent pi like this without the 0 if it is a hyperplane that doesn't pass through origin. Okay, so it requires both w and b. And what is the equation of the hyperplane? It is very simple. W dot x plus b equals to 0. This is the equation. So all the points, so the way you represent is all the points x such that, okay, oh, I have already written it here, sorry. Okay, so pi is basically, or a plane pi is a set of points or d-dimensional points such that the dot product with w plus b equals to 0. This is one simple way to define a hyperplane. right? So I'll be using this notation, and I'm assuming that W is a d-dimensional vector, B is a scalar, right? Again, we have discussed this in the course videos, right? And I'm always going to assume a d-dimensional space. So let's take this plane. For example, if you take this plane, again, the formulation is very simple. Imagine if I have a plane like this, pi 0, which is passing through origin, and I have my W here, again, passing through origin. Any point X on this plane, again, I'm just using a 2D representation here, but this is a d-dimensional space, right? So any point X here will be normal or perpendicular to W. So for pi 0, it is W transpose X equals to 0. Or you can also write this as it's a dot product of W and X. You can also write it as W transpose X. Just a different notation of writing it, right? So when I say dot, it means dot product, right? Very simple stuff, nothing fancy. Now, I have a question here for you. So if you were to represent, again, given this basic background, what is a good data structure you can use to represent a plane? How do you represent a plane? I would like to listen to your thoughts. Again, I'm seeing the chat window I'm also seeing the chat window here. So what do you recommend? What do you think is a good data structure to represent? So the question is simple, right? What is a good data structure? Again, we have studied data structures in Python, right? Basic data structures. What do you think is a good data structure to represent a plane? That's the idea here, right? So what do you think are good ways of doing it? Let me just check the internet speed. I hope there are no hiccups. Yeah, no hiccups. Okay. So I'm looking at the chat window on a different computer. So if anybody has ideas, do let me know. Somebody says list, okay. A list of weights, list or tuple list, okay, as x and y axis. Again, guys, this is not a 2D plane. This is a hyperplane. Numpy array, tuple. Okay, look at this. Okay, so everybody is giving some good ideas. So let's go down. Okay, so what do you need to represent a general pi? Okay, which may or may not be passing through origin. You need two things. You need W, which is a d-dimensional vector, and you need a scalar. Right? How do you represent this? Again, when you choose a data structure, very importantly, you should also ask what operations do you perform on it. The choice of data structure just should not be based on how you store the data. It should also be on operations. So you will mostly do vector operations, right? Like dot products, all of that stuff. So vector operations. You'll also be doing a bunch of matrix operations, right? So these are the typical things that you'll perform. So given that the operations that we perform are vector addition, vector dot product, multiplying this with a matrix, all of those things, what do you think is a good thing? So I'm just looking it down. So people say tuple, dict. Okay, let's take this down, right? So let's understand this. So some of you are suggesting list, okay? Most of you are suggesting list or tuple. Okay, so tuple. So how do you store the tuple? Okay, so would you store W1, W2? Again, let's assume W1 is the first component of this. Let's assume W is W1, W2, so on, WD. Okay, just for simplicity. So would you store it as WD, so on, so forth, sorry, W3, WD, comma B. This is one way to store it. But are tuples good with vector operations? Are tuples optimal for matrix operations? Right, so how do you do it? Okay, so if you think, again, some of you are suggesting very nicely, a good thing is actually Numpy. What is the purpose of Numpy? Numpy was designed for numerical operations on matrices and vectors. So Numpy array is a very good thing, because Numpy array is designed with the purpose of these operations, right? So Numpy array is designed with this. So if I represent W as a Numpy array, not an n-dimensional array, just a one-dimensional array, right? I can represent this as just one float, right? So the idea here is, as many of you rightly pointed, it's a very simple thing. It's a very simple concept, right? Nothing fancy here. Again, it should always depend on operations. If you represent it with a list or a tuple, one of the challenges you have is access to libraries. Again, we can always represent it with list or tuple, but then the operations that you perform, you have to write code for everything. Instead of that, if you do use a Numpy array, there is a lot of functionality that's readily available for you. Okay, so look at how I'm just representing it, right? So my W is this, okay, NP array. So I pass a list here. So the list is converted to an array. Very simple, nothing fancy. B is represented just as a float. Cool, I've just taken some numbers here. Now my pi plane can be represented as a tuple. So what I've done here, I've created a tuple of 2 elements. Okay, so I've created a tuple of 2 elements. The first element is a numpy array, The second element is just a simple float. Okay, the first element represents W, the second element represents B. So this is one way, because I need both W and B in many contexts, right? So very simple way. Again, see, I'm just creating a numpy ND array, but if I want to just store pi 0, what is pi 0? Imagine if my plane passes through origin. If this is my plane passes through origin, right? Then I don't require the B term, because the equation of my plane now is W transpose X equals to 0, right? So to represent that, I just need W. In such a case, what am I using here? I'm using a tuple. See, look at this. I'm using a tuple where the first element is a numpy array. The second element here is a float, right? I can also use the same representation with 0, or I can just say for pi 0, I don't require B, so I'll just represent it using just one numpy array. Very simple, right? Now, one interesting fact, okay? So imagine if I have 2 planes like this, okay? Just a quick question, okay? So just as observation, I should say, okay? Imagine if I have 2 planes, pi 0, which is passing through origin, and this is pi. If these 2 planes are parallel to each other, again, I'm just drawing 2D diagrams, but you can imagine them to be 3D planes. Beyond 3D, nobody can imagine, right? So imagine this. So this is one plane, this is one plane, right? Both these planes are, how do you say both these planes are parallel to each other? If this plane is represented just with W, and if this plane is represented using W and B, same W. So W is normal to this plane, W is also normal to this plane, right? So if 2 planes have the same normal, then they both are parallel to each other. Simple, very simple concept, nothing fancy here, right? Okay, cool. So just wanted to show you how to represent. Now let's go into some simple stuff. Okay, we'll do simple operations. Now if you look at our W here, our W is not a unit vector. Now what is a unit vector? Very simple concept that we discussed in the course videos also. Suppose take this vector W passing through origin. Take any vector. Okay, this is basically a vector W, right? So this vector W can have any length. So this whole thing, this length, the distance from here to this is called the length of W, right? So how do you get the length of W? You take the L2 norm of W, right? Or you take the Euclidean distance between this point and this point. Okay, that's also written as the L2 norm of W, right? We have discussed how to compute this. Now if I want, so given this W, if I want to get a W hat, which is nothing but the W hat is a unit vector, in the same direction as W. Okay, it's a unit vector in the same direction, as W. If I want to get that, so look at this, look at our previous definition. I just created a numpy array, right? So I did not ensure that its length is 1. I did not ensure that anywhere, right? I did not ensure that anywhere, very simply put. Now since I did not ensure that, if I want to create this W hat, which is nothing but a unit vector in the same direction as W. So what is a unit vector? Its length should be 1. The length of a unit vector is equals to 1. That's why it's called unit, because unit in math mostly means 1, right? In most of mathematics, right? So the idea here is, how do you compute that? It's very simple. So given any vector W, if you want the unit vector in that direction, again, we discussed this in the course videos. That's why I'm not going into the mathematical proofs. I wanted to show you the code walkthroughs more than math. So I've taken screenshots which are very similar to the course videos, and I'm trying to explain the math here. Okay, so that you get you can translate math to code, because once you do that, you can translate any math to code. Okay, one of the most important objectives of this code walkthroughs is to translate concepts and mathematics to code. Okay, so you have W hat equals to W by norm W. Basically, this is the equation. Okay, now how do we implement this in code? Okay, it shouldn't be very hard. It's actually fairly simple. Okay, so let me implement it myself from first principles using this definition. I'll also implement it using an inbuilt function. Let me show you both the stuff. Cool. So let's go step by step first. So I'm importing math here, nothing fancy, nothing complicated here. So First, I am computing the norm of W. I'm just computing this norm W, okay, which some people also called as the length of W. We use the norm terminology because in mathematics, in machine learning, we have L2 norm. We have lot of norms. You have L2 norm, we have L1 norm, right? We have Frobenius norm, right? So there is something called as Frobenius norm of matrices. Again, these are concepts that we'll encounter later in our course, and we'll revisit these concepts. Okay, I prefer to use the norm. I prefer to use the norm terminology rather than the length terminology because it's more widely used in mathematics. So the concept is very simple. So let's translate it into code. Okay, so what is W norm? W norm is, you take, say, what is the definition of W norm? You take W, do the dot product between W and W, right? Do the dot product, which is equal to W transpose W, right? And take the square root of it. This is the mathematical definition, right? This is basically, what is the distance between this point and this point? W minus 0, okay? Or this is origin, right? So subtract everything to 0, right? So you're just computing the distance from this point to origin. And how do you do it? Again, you can do it using, of course, you can implement the dot product also. Look at this. So what is this? As I just showed you here, this is this, right? Now you can implement this dot product or this W transpose W yourself also using for loops, but it's already available in Numpy. If you don't know what function to use, just Google this. Again, I'm trying to simulate what if I'm a beginner. I know the concepts. I know the mathematical concepts. How do I translate into code? Suppose if I don't know what function gives me dot product, I just say numpy dot product of vectors. I get some documentation. The documentation is for np dot dot. So given two vectors, it will do the dot product. Again, dot is a very general purpose thing. You can read the documentation here. I'll share this document with you. But if I do not know what function, again, it's almost impossible for anyone to remember every function that is there in Numpy, right? If I were a beginner, I would just simply Google search, find the right function, read the documentation as we have done in previous live sessions, and I will just do here. So what do I get? I get so what am I getting here with this? I'm getting this part, W dot W or W transpose W. Now on top of that, I have to do square root. We know math dot square root. So if you print this, what I'm getting here is this 2.6191 blah blah blah. Cool. Now I have a question, which is there some other function? Because Numpy, the whole of Numpy itself, Numpy and SciPy are designed for numeric and scientific computations. And in most of scientific and numeric computations, matrices and vectors are extremely common, right? Any part of mathematics, right? So I had this question. Is there some inbuilt function to compute the norm directly? Why should I worry about it? Then I just Googled this. Imagine if I were a beginner, okay? I would just say numpy norm of a vector, right? So I just get this documentation. Sorry, so let me just copy this. This is basically, okay. Again, you can just Google search it and you'll see all of this, right? So I read the documentation. You should always read the documentation. It says, okay, X is an array-like object. Okay, the odd basically means, okay, order of the norm. Now what all are possible? Non-zero, integer, infinity, minus infinity, fro, nuc. There are a lot of norms, as I told you, right? There is something called as infinite norm. Okay, there is something called as Frobenius norm, right? So there are lots of norms. So if you just go down, it says, okay, what is this? So if I use 2 here, it says, okay, 2 norm. What we want is a 2 norm, right? Or also called as the L2 norm. Again, here the definition of lots of types of norms that you can compute, right? So if you just, so 2 norm is what we are looking for. So what do I do now? I just say, okay, there is some inbuilt function. Let's just use it. So where is this function? This function is in Numpy module. Within Numpy module, there is a submodule called linear algebra. Within that, there is a function called norm, right? This is what we have to use. So let's go back. And I just say np.linearalgebra.norm w comma 2 because I want 2 norm. I just printed this. Now what do I get? When I want 2 norm, again, there are 2 ways of implementing it. One, we wrote it from the formula. Here what did we do? We wrote it from the formula. That norm w is nothing but square root of w dot w. We wrote it using the formula here. We wrote it using the inbuilt function, right? I just wanted to verify if both of them are same. Yes, they both look exactly the same. Cool. So in the future, I'm assuming that the Numpy guys have implemented it much better within C++. Again, whenever there is an inbuilt function, it's always a good option and a good idea to use it. In one of our previous live sessions, we have shown where we implemented code ourselves, complex code ourselves, and we used the inbuilt implementation. And we saw that inbuilt implementation, especially with respect to NumPy, SciPy, can be extremely optimal. Right? Again, here also, we are not writing the code from scratch. We are using some inbuilt functionality, which can be fairly fast and fairly quick. Right? So the idea here is this. Okay. Now, if I want W hat, what is the formula for W hat? We know that W hat is nothing but W by norm W. Norm W is just a real value. Norm W or W norm is just a real value. So what do? W hat is W by norm. That's it. So I get this now. I get this. Now, what is the property of unit vector? The unit vector's L2 norm should be equal to 1. Let's just verify that. Okay, so I printed the W hat. Okay, this is my W hat. But I also wanted to verify this. So what do? Again, we have this function which we'll keep using now whenever we have to compute norm. Okay, that's what we figured out using the Google search, right? So W hat 2, and I'm using NumPy linear algebra norm. And when I do this, this returns this print statement. And the norm is 1. That's it. So whether you use our own code or whether you use the inbuilt function, again, this is how you translate simple equations. The equations that we are learning here are very, very simple. Going forward, we'll encounter much more complex stuff. Okay, cool. Next very important operation that we perform a lot, right, is angle between two vectors. Right? So if you have angle between two vectors, if you want to find angle between two vectors, how do we do that? Again, we proved this in the course videos that if you have two vectors v1, v2, need not be unit vectors. If you have two vectors v1, v2, the angle between them, let's assume, is theta. Then cosine of theta is the dot product of v1, v2 by, again, if I just write this, if I don't put any number here, this basically by default means L2 norm, unless otherwise stated. If it is L1 norm, people actually put L1 norm here. If it is Frobenius norm of a matrix, people put F. If nothing is placed here, that means automatically the default norm is always 2 norm, unless otherwise stated. Right? So let's just get that clear. Okay, so we have derived this formula in the course videos. We have understood this very simple concept. This is literally high school level mathematics, nothing fancy here. Now let's take two vectors and actually translate this. Imagine if I'm given two vectors, how do I get the angle between them? Should be straightforward, right? It should just be cos inverse of this term. It should just be cos inverse of this, right? So that shouldn't be too hard. Again, okay, let's go step by step. Okay, let's create two random vectors first. Again, I'm just creating a random seed so that every time I run this function, I run this snippet of code, I get the same values. Then I'm creating two random vectors, v1, v2. Again, random vectors will play a very important role when we learn about other concepts like locality sensitive hashing in k-nearest neighbors. Right? So there is a concept called as locality sensitive hashing, which is basically a randomized algorithm which uses the concepts of random vectors. Right? Again, we'll revisit the concept of random vectors when we look at locality sensitive hashing in the context of KNN later, when we do a live session on KNN itself, or probably multiple live sessions on KNN. For now, what we'll limit ourselves to is, let's assume I have two vectors v1, v2, if I want to get the angle between both of them. It should be simple, right? Again, I'm just implementing it from first principles. I'm saying math.ACourse. ACourse is nothing but cos inverse, right? And what do? Dot product of v1, v2. Look at this, dot product of v1, v2, same thing. Again, this is literally very simple translation. Divided by norm of v1 multiplied by norm of v2. Again, NumPy gives me, NumPy and math give me all this functionality. Remember, whatever angle you get here, angle 1, 2 is in radians, not in degrees. Okay. Most scientific computations are done in radians and not in, they're not done in degrees, right? Very important. Okay. Cool. Okay, okay, I'm happy that some of you are answering questions in the live chat window. Very happy about it. Thank you, folks. Somebody is asking this question: do we use cross product anywhere? Do we use cross product, not the dot product? Remember the cross product that you have learnt in physics in your 11th and 12th class, right? If you remember, we had this F equals to BIL, right? in electromagnetism, F equals to BIL. I forgot how to write this. This B is a vector of magnetic. I think this is how it looks. This is the length of the, this is the BIL, okay? I think this is sort of the formula. I forgot. It's been a while I looked at these formulae, right? So you have the right hand thumb rule and all this. So cross product is not very often encountered in machine learning and deep learning and all the concepts, but it is something that is used in physics a lot. Dot product is what we use extensively because we want to find angles between lines or angles between hyperplanes, all of that stuff much more extensively in machine learning. We don't use cross product much. Okay, angle is always in radians by default, always. Okay, because all of scientific computation happens in radians and not in degrees. Okay, in any scientific computational library, all angles are represented in radians by default, right? So yeah, it's F. So yeah, as somebody rightly pointed out, I think just let me Google it. It's been almost 20 years. I saw this, almost 20 years. F equals to BIL, right? So I think there is a cross product between, okay. I think there is a cross product between B and, where is this? Okay, there is sine theta, that's the intensity, but where is the direction? Okay, I think it is, okay, B is the flux density, B is flux density, F is force in newtons. Okay, yeah, there is cross product somewhere here if I recall, force on a current in a magnetic field. Oh, this is school level physics, cool. Okay, BIL, the reason you have sine theta here is because of the cross product and not the dot product. Oh, there is this, yeah, right hand rule. I think it's called thumb rule or something. Oh, so look at this. So yeah, it's encountered in physics a lot. We know that, right? I forgot the exact formula from 11th, 12th class math. It's been years I've done it. Okay. Sounds good. Yeah, somebody says F equals to IL cross B. I'll take your word, assuming that you're an electrical engineer who knows this much better than us. Okay. We have after our 12th class, I've not encountered this myself. Okay. Cool. So let's go back to data science specific stuff. Okay. Cool. So the other thing, right? Given up, suppose if I have a hyperplane pi like this, which I'm not saying is passing through origin or anything, it is represented by W and B. Okay. General pi. When I say pi 0, only then it passes through origin. If I just say pi, it is always parameterized using W and B, both. Okay, and let's assume W is the normal to this. There is a point X. What is the distance? What is this distance from X to this? Again, this is something that we use a lot, whether we are doing logistic regression, right? Whether we are using linear regression, whether you are using support vector machines, all these techniques, this mathematics is extremely important. Lot of machine learning techniques that we encounter a lot, they try to find a plane. And to do that, distance from a point to a plane is very important. Again, when we do the logistic regression sessions, linear regression and SVM, we'll see this reoccurring again and again and again, right? Cool. So first let's learn the basics. What is the distance here? Again, we have proven this in the course videos using a very simple diagram, etc. The distance is absolute value of W dot X plus B by norm of W, because I'm not saying that W is a, I'm not saying that W is a unit vector. If W is a unit vector, if norm of W equals to 1, then the distance here is just W dot X plus B absolute value. Why are we putting the absolute value here? Because distance is always positive. Okay, so that's why we are putting the absolute value here, right? So again, let's just create some random planes and random points and compute the distance. Okay, cool. So what am I doing here? I just wanted to show how to translate this simple formula to equations. It's very, very simple actually. Okay, again, I'm just creating a random seed and I'm creating this W, which is a 6-dimensional vector. Look at this, W is a 6-dimensional vector. B is just a real valued number and I'm creating a random point X. Okay, so using this W and B, I'm getting a plane pi. Right? Using this X, I'm getting some point X. Okay. So now using this, I can compute the distance using, I'll just translate this formula that we have seen. It's a very simple translation. It's just simply translating this formula to equation. Again, Numpy gives you most of the heavy duty stuff, right? We don't have to worry about it. Again, for the mathematical proofs of this, please look at the videos that we have posted as part of our course videos, publicly available to everyone. Please go check out those videos for proofs of this. Again, I requested you to do that before the live session itself, right? So I'll not be covering those mathematical proofs and details here. Cool. So how do you do it? It's very simple. Again, I'm covering the basics. We'll keep going to more complex cases as we progress, right? So it's actually very simple. Now let's look at this, right? So what is the formula? W dot x plus b. So it is basically dot product of w and b plus b in the numerator. In the denominator, it is norm of w or L2 norm of w. Okay, I think I did not reconnect. Okay, I hope it reconnects and everything works. It does. Okay. If you don't have enough activity for, I think, a few minutes, Colab automatically disconnects. There is a way around that. I can change the JavaScript here to make sure that it doesn't die. Okay. There are some hacks around it. Cool. So very simple. I have the code here. It works. Okay. So I've simply translated what we see here. Very simply, the equation that we see here, I just wrote it as one simple line of code. Now the big question that I have here is, you have written this code, okay, seems logical. How do you test this code? Again, as I mentioned in the previous live sessions, for any problem or any snippet of code or any function you write, right? How do you test it? Right? How do you test it? How do you test that this code actually works? Or maybe you've done a small mistake. Instead of plus, you wrote minus and everything goes for a toss. Instead of norm 2, you did norm 1 and everything goes for a toss. How do you test this code? Again, you can, for most of this functionality, you can just, yeah, somebody's asking about random seed. So what random seed does, let me just explain this. You can give, so random seed, I've explained this in the previous live sessions also, but let me just repeat it quickly, right? So random seed, I can use any number here. This basically, so your random number generator, also called as pseudo random number generator, pseudo random number generators that you have in most programming languages and in most libraries, they generate a sequence of numbers. So every time I run this code, if I did not have this line, every time I run this code, I get a different set of random numbers. Right? I get a different set of random numbers. By using this line and fixing the number always the same. So this number says intuitively, again, I'm not telling you how, in this context, I'm not going into the depths of how pseudo random number generators works, how seed works. I'm not going into the mathematics because that's a fairly in-depth mathematical discussion onto itself. But intuitively what it does is very simple. The moment you set this to 100, okay, next time whatever numbers you generate, every time the same numbers are generated. This is like ensuring that the random number generator starts at some specific point. You can think of this point as 100. From this point, so when I say seed equals to 100, it will always go to this point in a sequence of random numbers, and it will always generate random numbers from that location. Think of it, I mean, that's the easiest way to think about it. So this is written so as to ensure that every time I run the code, I get the same random numbers. Otherwise, when you run, you get different random numbers, I get different random numbers and things like that. Cool. So how do we test it? Okay, let me see. Okay. Pass the known values for testing. Can you suggest me some good known values, folks? Again, you can use any seed, guys. You can use any seed. You can use 10, any number. Just look at the documentation for NP random seed. You can use any number here. Just fix that number every time you're running it. That's it. Yeah, you can use random state, random seed. All of them do mostly the similar stuff, right? So don't worry about it. Again, I'll try to answer only questions which are in the context of the discussion for now because we are in the middle of it. Pass the known values for testing. What are some simple values that you can pass? D greater than 0 because W and X are in the same direction. No. Somebody is mistaken here. Look at the code that we have written. There is an absolute value here, which means D will always be positive. I just mentioned this a few minutes back, right? D I am placing because the distance is always a positive number. We'll come to half spaces, we'll come to which side a point is little later. Okay, please don't confuse those two now. Oh, so somebody says 2D, 3D point, you should give dist blah, blah, blah. Okay, so this is, so for dot product also, why do you need the distance, this thing for dot product? Because you're taking, you don't require for dot product, right? Why do you need absolute value for dot product? You don't need it. So okay, so where were we? Okay, so how do we test this? How do we test this very easily? Okay, some simple test cases that you guys, W22 from origin. Okay, that's a good idea. Okay, just write a function for this and pass different vectors. That's a good idea. One simple thing that I'll suggest you is this. Look at this. Very simple suggestion, right? Again, this is a 6-dimensional, remember this is a 6-dimensional vector. So my vector W is such that the x-axis, the first axis, so this is 6-dimensional. Of course, I can't draw 6-dimension. I can't draw anything more than 3D, right? Suppose let's say in the first dimension, second dimension, third dimension, there is 4, 5, 6 dimensions also somewhere. So I'm creating my W such that my W only is on this direction. Look at this, my W is such that its length on the first dimension is 1, rest all dimensions is 0, which means it will be on this axis. If you think about it, it will be on the axis corresponding to the first dimension. Now, if my X is also on the same, so again, you can test it in many ways. If you want to test it in high dimensional space, this is one simple technique. So my W is, again, remember that norm W here is 1 for me. Cool. Now, look at this. I'm also choosing my X such that my X only has component in the first dimension. All the other dimension components are 0. So which means where is my X? My X also will lie in this on this axis only, because rest of all the axes 2, 3, 4, 5, 6 axes are all 0. Right? So what happens now? What should be the distance of X now? Look at this. So what should be the distance of X from W? That's what we want to compute, right? What should be the distance of X from W? Right? Very simple. I hope the question is clear. Right? So I'm representing my plane. Remember, so instead of saying distance of X from W, let's say distance of the plane represented by W. So my plane has this normal. Look at this. Let's imagine this in 3D first, because 6D is anyway impossible. So imagine I have only 3 dimensions here. My W is represented like this, which means where is my plane? My plane is actually here, right? Which means my plane is actually here. My plane is the axis that my plane is spanned by, or my plane is this plane which has vector 2 or axis 2 and axis 3, because this is perpendicular. Again, I'm trying to draw a 3D diagram here, right? So this is my plane now, right? Now my X is here. So what should be the distance of X from the plane? It should be the distance on the X axis itself. The distance should be 23, right? Again, this is one simple case that I'm building here, right? The distance should be 23. Again, you can write lots of simple test cases like this. I'm trying to show you how to think of test cases in d-dimensional spaces. The easiest one is to test cases in 2D and 3D spaces. That's easier, because you can simply come up with something that you can visualize easily and do it. But you can also construct examples in high D spaces like this, right? So you just do that and the answer should be, okay, so where is this? Oh, it got disconnected. So let me just run this once. So let me run the snippet of code. The answer should be 23, as I just explained a while ago, right? The same concept that you can imagine in 2D and 3D scales to 6D, right? Especially with respect to planes and distance from planes and things like that, right? The very simple case. Now somebody was saying about half spaces, right? So what is the concept of a half space? Look at this. Imagine if I have a plane like this. I have a plane like this, which is represented using W and B, right? And my W is pointing in this direction, let's say. My W is pointing in this direction. Now, all the points which are there on this side of the plane, all the points that are there in this side of the plane is called one half space. It's also called as positive half space. Because this plane effectively, this plane is breaking the whole space into two half spaces. Look at this. This plane doesn't stop here, right? This plane just keeps going on like this. This plane keeps going on. Given this whole in 2D space, this is breaking the 2D space into this space and this space. The space towards which W is also present or W is pointing to is called the positive half space. The other side is called negative half space. We have discussed this in the course videos also. Now, given any point P1 or P2, how do we determine whether a point is in positive half space or negative half space? Because again, this concept is very, very important when we do logistic regression, when we do SVMs and concepts like this, right? These concepts will play one of the most important roles when you learn machine learning algorithms. Again, I'm not teaching everything randomly. I'm trying to limit myself to concepts that we encounter again and again in machine learning. So this is like the basics that you need for future stuff, right? So again, this is very simple. It's a very similar formulation like earlier. It just says, okay, so given this P1, I just take W dot P1 plus B. If this is greater than 0, look at this. If this is greater than 0, then it is in the positive half space. Okay. If this is less than 0, W dot P2 plus B, if it is less than 0, it is in the negative half space. If it is exactly equals to 0, it is on the hyperplane. It is on the hyperplane. Because all the points here, look at this, all the points here, like if I have a point P3 here, okay, so let me write it as P3. Okay, if I point P3, this will be equal to 0, right? That's a definition. That's a definition of a plane as we discussed and as we derived it. And again, why is this so? We have discussed in the course videos. I'm not going to repeat that proof here. But this is the general idea, right? So let's see. So somebody says if angles are in 90 degrees, I didn't understand. What about if plane is not on a particular axis? Again, so again, this is just a test case that I've shown you on how to test that the code we have written is correct. The test cases, we'll try and pick the simpler test cases. If you want more complex test cases, try it in 2D and 3D. In higher dimensions, you can't even visualize what is happening, right? So coming back to the half spaces concept now. Okay, so let's just do it. Okay, so it's very simple. It's very, very simple. The logic is also very, very straightforward. Okay, let me just erase this. The idea is as follows. So I'm just generating again a random vector W and B. So this generates a plane pi. So both of them generate a plane pi. I'm generating a point X, right? Just randomly, right? Now I'm saying, okay, what is the formula here? Dot product of W and X plus B divided by norm of W. Oh, sorry, I forgot to mention this. Okay, so this by norm of W. I keep assuming that W is a unit vector, right? So the right thing is assume if W is not a unit vector, you have to divide it by norm W. But again, this division doesn't change the sign. Let's not forget, this division doesn't change the sign, right? That's important because norm W is always positive. This is always positive. So this will not change the sign, right? So you can actually skip this whole thing if you want. Nothing will change. Okay, cool. So by doing this, and again, I'm using the Numpy sign. Numpy has this function called sign, and which will give me whether it is positive or negative. Okay, so I've just taken some random hyperplane. I've just taken a random point, and it says that this is on the positive side. How do you test this now? Again, it's very important. Whenever you write anything like this, it's important that you test it. Right? Again, it's very simple. If you think about it, there is a very simple way to test it. Okay. The idea is this. Okay. Suppose I've taken a random hyperplane like this. Look at this. I've taken a random hyperplane. I have a W, right? And I have a B also associated with it. My B is 1.2. Okay. If the point that I have, look at this, the point that I have is origin. Okay. Look at this. The point that I have here is origin. Right? Very simply put. Okay. The point that I have here is origin. Now we know that, okay, so if I plug in, if my X equals to origin, what does W transpose X plus B will be equal to? If X is origin, which means X is equal to 0, right? If X equals to 0, W dot 0 is 0. So this will become just B itself, right? So whatever is the sign of B, look at this, whatever is the sign of B, that is the direction in which origin is. If I've taken B equals to positive value here, if I take B equals to positive value, right? If B is positive value, my origin lies on the same direction as my W. If B is negative value, then my origin will lie in the opposite side as compared to W. Very simple concept. So for test cases, you can use these boundary cases to test if everything is working all right. So if I choose B as positive value, I get positive. If I choose B as negative, I get -1. Again, it's always a good idea, all the functionality that we are writing, whether it is distance between a point and a plane, all of these things, try to implement all of these snippets as functions so that you can reuse them in the future. Right? I'm just writing it as simple code just to show you. Right? Very simple concepts, nothing very fancy. Now let's go on to some simple matrices. Okay, with the basics out of our way. Again, one of the biggest applications of matrices, right, in whole of data science is to represent data matrices. Again, we'll see what data matrices are in the future live sessions. Again, some of the concepts are also available in our course videos. If you just go to our course videos, go here, linear algebra, there is this chapter called as dimensionality reduction and visualization, where we discuss about the basics. Again, wherever you have the I symbol, all those are freely accessible. Again, I think in these videos, we give you basics of what is a data matrix, what does basic feature normalization, what is column standardization. We discuss some of the basics in the context of a very popular dataset called the MNIST dataset. So here is where you can watch some more videos about how matrices are represented. Cool. And matrices are used a lot to represent the data matrices, just like our pandas. If you recall, in pandas, we represent everything like a matrix where each row represents an object, each column represents a feature, if you recall, right? Again, if you don't know this, that's okay. We'll cover this in the future sessions also. Some of the most basic operations that we perform are simple: addition, multiplication. We have covered this, right? In the past live sessions, I've shown you how to add two matrices. I asked you to implement how to multiply, but you can do all of that in Numpy. You don't have to implement it from scratch because Numpy does a very good job at it. Then I wanted to introduce you to a couple of very simple concepts called as Frobenius Norm and Hadamard product. Okay, they're just fancy names. They're very simple concepts, right? So, okay, so this is not there. I forgot to remove it. Okay, this I thought I'll cover it in the future sessions. Okay, cool. So let's go step by step. Okay, very simple, nothing fancy here. So what I'm doing right now is I'm creating a data. So look at this. I want to create 10 points, each point of 4 dimensions. So I always use, in my notation, I always use to represent number of data points. So number of points, I always use D to represent the number of dimensionality. That's a standard notation, which is also followed extensively in in books. But just to be sure, I try to stick to the single notation, right? So what am I creating here? I'm creating 2 matrices. Again, I'm just creating random matrices. In the future sessions, we'll actually load real data. Oh, actually, you don't have to worry about it. There is one example here where I load real data and show you the data matrix, right? So, okay, so I'm just creating 2 random matrices, x1, x2. I'm also creating a d-dimensional vector here, okay, random vector w. I'll show you why I do that. There are a bunch of operations I wanted to show you how to do in Numpy. Cool. First, let's print x1, x2. I'm just printing them, okay. So this is my x1, right? If you notice, 10 rows, 4 columns, just random data. This is my x2. Now, if I do this operation, if I do x1 plus x2, so x1, the way Numpy works is, remember that x1 and x2 are ND arrays, right? x1 and x2 are Numpy ND arrays because they're 2-dimensional arrays. W is just a Numpy array because it's a 1-dimensional array. It's a vector. Now, the plus operator can work on Numpy arrays. When you do plus operation, what it returns is the sum of 2 matrices. Again, we can verify that. Take this, take this. If you sum both of them, you should get a value something like 1.2 something, right? Look at this. First row, first column, first row, first column. If you sum both of them, you should get 1.2. So again, I just printed x1 plus x2 and it actually prints x1 plus x2. You can just pick a few points from x1, x2, match them, they look the same. For example, look at this, 0.42, 0.58. The sum should be close to 1, right? And the sum is close to 1, right? So I've just printed x1 plus x2. Now, just like plus, if I do x1 star x2, because star is what we use to multiply numbers, right? So what does x1 star x2 do? It does something called as element-wise product. It doesn't do the typical matrix product that we learned in school. So what it does is, imagine if I have 2 matrices like this, right? The element-wise product, which is fancifully called as Hadamard product, just a fancy name for it. You could have just called it element-wise product. It takes this first element, multiplies it with the first element and returns that. So if this is matrix A and if this is matrix B, what this product or element-wise product or Hadamard product does is, Aij is multiplied with Bij. Again, remember, they both are scalars, right? Aij is just a number, Bij is just a number. This will be equals to Cij for all I comma j, right? So Aij is the value that is in ith row and jth column, right? In a matrix. In a matrix, Aij basically means the value in the cell that is represented by ith row and jth column. Similarly, Bij is ith row, jth column. So each element corresponding to the same element that is there in the other matrix, it just does a element-wise product and returns it. And for this, both x1 and x2 should be of the same size. Look at this. What is x1? x1 is n cross d. x2 is also n cross d. Because they both are of the same size, this product is fully valid. No issues with it. Cool. But if I want to actually do x1 dot x2, the matrix multiplication, remember the matrix multiplication that we learned? First row is multiplied with first column to generate the first, to generate like this is the first row, first column. This generates this first element now. You do a dot product between, you basically do a dot product between this vector and this vector and you get the first element. The typical matrix multiplication that we learnt in school, if you want to do that, you have to use matmul in Numpy. If you do this, you do not get the actual matrix multiplication. What you get is element-wise product. We see a lot of students who use this and they expect actually Numpy's matmul. This is a very, very common mistake that we see people doing in our assignments. Very common mistake, right? Because we all are used to represent things by star. Again, this does not throw an error. Everything works, right? But things start breaking down. But here there is a problem. If I execute all of them, look at this. What is x1, x2? I'm trying to multiply x1 and x2, right? So x1 is n cross d. x2 is also n cross d. Can you multiply these two matrices? This is d, this is n. They both don't match. So this should actually throw error, right? If you think about it logically, right? So let's actually see this, right? Okay, so I actually get an error and it says very clearly matmul input operand 1 has a mismatch in its core dimensions, right? Oh, somebody is asking a question. So somebody is asking a question, which is why the random numbers are always in float and not int? Because rand function generates floating point values. There is another function called randint, which generates integer values. Okay, it all depends on what function you are using to generate the random values. So another very interesting question is what happens if you have tensors? Okay, all this is good with matrices. What happens when you have tensors? What is a tensor? Again, we have discussed this in the previous sessions also, right? This is a vector, right? So this is a vector. This is a matrix. A matrix is a two-dimensional structure. A tensor is a three-dimensional or more dimensional structure. Now we will see tensor multiplication when we come to the context of it. Okay, tensors we learn when we come to deep learning, especially using TensorFlow and Keras, right? So we will cover how tensor multiplication works when we do sessions on, again, we'll do some basics of tensors. Again, it's a fairly simple concept, you can pick it up, but I did not want to do it here because they're just overwhelming students now. We'll surely cover how tensor multiplication, how tensor operations work when we get into the context of deep learning. We'll surely do that in the future sessions, right? So yeah, as somebody pointed out, so there is an error here, right? So what is a simple fix for it? It's simple, right? So you can just do transpose. So it's so easy. Again, Numpy does this so beautifully. All the mathematical operations in Numpy are like godsend. So when you do x2 dot t, it just transposes it. So now x1 has n cross d, x2 dot t, which means transpose of it has d cross n. Right, now I can multiply because these two numbers match. And what should be the result? Again, remember that n equals to 10 and d equals to 4 for our example. Right? So when I multiply them, the answer should be an n cross n matrix, which means it should be a 10 cross 10 matrix. I just printed the shape of it. Again, you can get the shape of any Numpy matrix by just saying dot shape. Very simple, right? Again, these are common mistakes that happen. That's why I just wanted to cover it quickly. Cool. So the next thing is if you want to multiply a vector with a matrix. Again, this is one of the operations that we perform a lot in when we actually start modeling things. When we start going into machine learning models, we want to multiply a vector with a data matrix. So let me show that diagrammatically first. Okay. Suppose imagine I have an n cross d matrix here, right? If I want to multiply it with a vector, this vector should be of d cross 1. Okay, this is my matrix, let's say this is my matrix x1, this is my vector w. When I multiply both of them, what do I get? I get an n cross 1. So what am I getting here? I take each of the rows here, Again, different books and different blogs and different research papers might use different notations, but concept is the same. So you take a row here, you multiply it with a column. Again, so this is the proper matrix vector multiplication. Right? This is a column vector. Here I have a matrix where each row represents a data point or each row represents something important to me. We'll see that in the context of data matrices a little later in the future live sessions. So this multiplied by this, I get the first value. The second row multiplied by this, I get the second value, and so on and so forth. Right? Now again, here very, very common mistake is dimensions messing up. Right? So let's see. So first I wanted to check, okay, first I wanted to see, okay, np.w and x1's 0th row. Look at this, I have my x1, right? My x1's 0th row. I'm taking my x1's 0th row. This x1's 0th row is basically a d-dimensional vector, right? So this is basically a d-dimensional vector. This x1's 0th vector, I want to do a dot product with w and see what the value is. So dot product of w with x1, 0th row, all the columns. So I get this value, right? Cool. Now I want this value to match with what I do when I do, so look at this. I can use matmul. Matmul not only multiplies matrices, it can multiply a vector with a matrix also. So what am I doing here? Look at what I'm doing here. Again, you should always make sure that dimensions match. So I'm multiplying w with x1 transpose. What is w? Okay, look at this. You should, again, the moment I run this, okay, if you print this, look at this. If you print this, you get this output, cool. So I'm multiplying w with x1 transpose. When I do w with x1 transpose, again, you should always make sure that things match. What is x1 transpose? x1 is n cross d. So x1 transpose is d cross n, right? I'm multiplying this with w. So what is w? W is, again, in most of mathematics or even in machine learning, matrices are assumed to be column matrices by default. Everything is assumed to be a column matrix, right? So what is a column matrix? You have, okay, so again, we have to be very, very careful on the shapes of things. This is one of the most common mistakes that we encounter, right? So if you write this way or if you write this way, it will work. Okay, so here w, in Numpy, the w is represented as 1 cross d, one row, and so it's not represented as a column vector. This w here in Numpy is represented as a row vector. So one row and d columns. So that's why when I do a dot product between, so when I do a mat multiplication between this and this is working. This will work, right? Remember, if w is a row vector of 1 cross d, this will work, right? So when I print this, I get this answer. Now just check the first value that we get here. This value matches this value as it should. This value and this value should match, right? Because obviously the first row, when I multiplied with w, I got this result. That result should be in the output also, the first cell should be that value. Now I could have written this differently also. Look at this. If I wrote it this way. Now what is x1? My x1 is n cross d. My w dot transpose. Okay. So my w dot transpose is, so my w is 1 cross d. So w transpose is d cross 1. Now this will also work. So whenever you are doing this, just make sure whether w is a row vector or a column vector. Just make sure. Numpy uses row vectors. Mathematics guys use column vector by default. That confusion can kill you. Right? I've seen, I mean, this is a very common problem. People try to do this. Suppose if I just did this. This will throw an error because w is a 1 cross d, x1 is an n cross d. So this will throw you an error. So the moment things throw an error, just make sure that you write what it is. It's always important when you're translating this into equations, always check for this sanity. I mean, I do it even today after many, many years whenever I'm writing matrix multiplication, because this is one of the most commonly used things, whether it's matrix multiplication or tensor multiplication, right? Please make sure that you don't mess up these dimensions, right? So whether you write it this way or write it this way, you get the same result. But the moment you write it this way, again, you get this very common error, which is, okay, input operand mismatch in dimensions. Basically, this is the typical error that you get. The moment you get this, make sure to write these equations. Very common mistakes that people do is they don't write these equations. They don't write this and clearly understand whether w is a row vector or a column vector as represented in Numpy and mess up things. Very common mistake. So please be careful. Okay. Then there is this concept called as Frobenius Norm. Okay. Frobenius Norm, again, this is one fancy name given. What does a Frobenius norm actually mean? Imagine I have multiple entries in a matrix A. Suppose I have a matrix A and I have multiple entries. I take each entry here. Look at what we do in L2 norm. Given a vector, look at this. If I'm given a vector, what do? We square each of the elements. Right? We sum up everything and we take square root. Basically, that's what is your L2 norm, right? That's what is your L2 norm. So the same concept of L2 norm, if you extend it to matrices, what do you get? Take each of the elements that you have in your matrix. Suppose if my matrix is A, right? Take each, so I throw jth column, this cell is called Aij, right? This cell is represented as Aij, right? Very simply put. So for all I and j, I goes from 1 to n if you have n rows, j goes from 1 to m if you have m columns. If this matrix is an n cross m matrix, take every element, square it. Sum this up across all the rows and columns. Basically, you're taking all the elements that are there in the matrix, taking the square and summing up all of them. And you're taking the square root of it. That's what is called the Frobenius norm. Again, this definition is valid if you have real numbers in a matrix. There are complex matrices that we do not encounter much in machine learning. But complex matrices are used in electrical engineering, electronics engineering, even mechanical engineering, etc. Right? So if you have a complex matrix, what is a complex matrix? Where the entries can be complex numbers, right? For example, suppose complex numbers, right? We know I, which is square root of -1, right? So complex numbers have a real component. For example, this value is, let's say, 3 plus 2i, right? So Frobenius norm can also be defined on complex matrices, wherein the definition is slightly different, but we do not use complex matrices much in machine learning. But Frobenius norm is a concept in linear algebra. Again, remember, linear algebra is used in many places, not just in machine learning AI. We are limiting ourselves to the discussion in the context of machine learning and AI, right? Again, Frobenius norm is used in machine learning for some errors. We actually use the Frobenius norm in our course videos when we learn about non-negative matrix factorization. Okay, there is a whole chapter called recommender systems, where we learn about the concept of non-negative matrix factorization, which is again a concept that is also taught in some linear algebra advanced courses, where this Frobenius norm is encountered. I'm just connecting the dots for you, right? So I can get Frobenius norm very easily. Look at this. If I have a matrix x1, I can get the Frobenius norm by just using the norm, because we saw this definition earlier, right? So the linear algebra norm in Numpy can compute lots of norms. We saw that a while ago, right? So the linear algebra norm can compute lot of norms. If I just give FRO, it computes Frobenius norm. If I give 2, it gives 2 norm, right? So this norm can compute norms on vectors as well as matrices, right? It can be 1D or 2D. Look at this, X must be 1D or 2D, not for tensors, right? So what do we do now? We just say Frobenius norm, we print it. What value do we get? Look at this. We get a value which is 3.54. But let us also implement it. Again, to understand a concept in depth, it's always a good idea to implement it. So I'm implementing the formula here. What does the formula say? The formula is very simple. It's right above here. For all I, for all rows, for all columns, take the square of each of them, sum up everything and put in a square root. Right? We have seen how to do simple for loops, right? In the previous sessions. So I get shape. So given x1, I get the shape of x1. I'm printing the shape. x1 is a 10 cross 4. We know this. x1 has 10 rows and 4 columns. We know this already, right? Because we just created a random matrix like that. I'm creating a sum here for I in this, right? When I say x1.shape, what does it give? It gives a tuple. Always remember what is the data type that is given. I get a tuple. So if I take sh0 should give me the number of rows. So what am I doing? For I in rows, for j in columns, because I'm using sh1 here, all I'm saying here, to this sum, keep adding xij square. Just keep adding xij square. Now at the end, I'll just take the square root and print it. I get the same value here, except for small rounding error, right? So this is 896, this is rounded to 19, right? So whenever you have a concept like this, it's also a good idea to implement it so that you understand better the concept. It's always a good idea. And of course, in practice, when you're writing production quality code, I would rather use this instead of writing my own code, because as we have shown earlier, this is going to be slower than inbuilt code, because inbuilt code is optimized using C, C++ in Numpy. Cool. So the next operation that we'll go into is convolution, right? So yeah, somebody is asking about where we use Frobenius Norm formula in machine learning. I just mentioned this a while ago, right? We use it in non-negative matrix factorization. Cool. One digit in Frobenius formula. What is one digit? I didn't get what one digit you're talking about. Why we are getting one extra digit in the Frobenius formula? Again, you can all this, if you want more digits in the decimal value, you can always get it, right? So this print is just rounding it off and printing it. You can always get more digits if you want. That's not a problem. Cool. Okay, by default, W is a column vector. Yes. So importantly, in whole of, again, there is this dichotomy that W in mathematics is always taken as a column vector, right? In mathematics, in most of mathematics. But please also remember that it depends on the implementation. The way a NumPy, again, how did we represent W here? We represented using NumPy array. NumPy array creates a row vector by default, not a column vector, because it is trying to represent an array, not a vector. Remember, NumPy does not have, NumPy, what we used, what class did we use, or what object did we use to represent W? We are using NumPy array. NumPy arrays are row vectors by default. So we just have to be careful with the dimensions when we are writing NumPy based code. That's it. Otherwise, mathematicians or even in our course videos, we assumed that all vectors are column vectors by default, right? So, okay, sounds good. Okay, so let's go to convolution. I just wanted to show you the power of matrices in the context of image processing. Again, please understand that this is not whole of image processing. We are just touching the iceberg. I just wanted to show you an application so that you can connect the dots here. Convolution as an operation is used extensively in whole of deep learning and computer vision a lot. Again, there is a whole network called as convolution neural network, which is based on the operation of convolution. But convolution as an operation is actually studied in signal processing. Look at how the whole thing is connected. It is the electronics engineers and signal processing guys who actually came up with the concept of convolution, right? So the image processing guys, right, the people who are doing image processing work, they borrowed this concept from signal processing. The concept from image processing was taken to computer vision, which is now used in deep learning. So this concept of convolution, again, the convolution operation from signal processing, they also borrowed it from applied mathematics, from linear algebra. Okay, they borrowed it partially from linear algebra, partially from calculus, right? So the signal processing guys who know signal processing, there are many ways of looking at convolution, right? So here we look at something called as discrete convolution, or we look at convolution in the context of image processing and computer vision, not from a pure signal processing perspective. That's a different beast altogether. Okay, so let's look at this, right? So what does convolution do? Again, I'll show you a very simple example of convolution, how it's powerful, but I want to explain the power of matrices in the real world, right? So let's look at a very simple example here. Cool. Let me use this. Okay. Suppose, imagine if this is my image. What is an image effectively? Let's take a simple black and white image, also called as grayscale image, right? Simple image. Color images we'll learn later. Okay, it's slightly more complicated. Let's take the simplest grayscale or black and white images, as we often refer to them as in colloquial English in India, but they're technically called grayscale images. An image is actually a bunch of rows and columns. An image is actually a matrix. An image is basically a matrix. Suppose if I have an image which is 500 of size 512 cross 512, what it means is I have 512 rows and I have 512 columns. And each of these cells contain a value which says how bright this pixel should be. This is what is called as a pixel, right? Each of these is called a pixel. This is how your monitors, your screens, everything also work. Each of these is called a pixel. If you have a grayscale image, which means you don't have color here. Each of these values, so a grayscale image can be represented as a matrix, where if you have an image of 512 rows and 512 columns, or this is the image size, every cell has a number. Every cell has a number inside it. So you can actually think of an image as a matrix. And all the beautiful mathematics of matrix algebra can be applied on images for image processing and computer vision. One such operation is called as convolution. Okay, convolution is a very beautiful operation. It can do a lot of things. Okay, we'll look at one simple example. Suppose, imagine that this is my image. Okay, so again, just to give credits, I've taken this image from the Apple's developer blog. It's again, I try to use all the URLs here so that I'm fully transparent about it. I did not draw this. Okay, so other diagrams, yes, I drew them and I put it here. So imagine if I have this image, each of these is a pixel in image. Let's assume I have a grayscale image. We'll see how everything works if you have color image when we learn about tensors, when we learn about convolution in the context of tensors, etc. That we'll see later, right? So if this is my image and each of these is my pixel, now this thing is called as a convolution kernel. A convolution kernel is also another matrix. Look at this. This is my image matrix, right? Let's call it as IMG. Okay, I have something called as a kernel. It's also called as a convolution kernel. Okay, so please don't confuse this kernel with kernels in SVM. Those are different concepts. This name came from image processing. Okay, so remember that a kernel is a smaller matrix, right? So again, let's assume this kernel is a K cross K matrix, right? My kernel, let's assume, is a K cross K matrix. Imagine that my image is, let's say, some D cross D image. Okay, D rows and D columns. Again, need not always be same dimensions, but I'm just taking it for simplicity. Now, what does convolution operation do? So, convolution operation, it's also called as 2D convolution because there is a concept called 1D convolution also. There is a concept called 3D convolution also. First, let's look at 2D convolution. We'll learn about others when we learn tensors, etc. In deep learning, we'll learn all sorts of convolutions. So, conv2D takes an image, right, and it takes a kernel. It takes a kernel as input and it generates an output. Again, this is my output here. Look at this. This is my output. And how does it generate the output? It takes, look at this. Suppose it has this pixel, right? Corresponding to this pixel, look at this. My kernel here is 3 cross 3. Corresponding to this pixel, look at this. This pixel is third row, third column, right? So it takes one pixel here, third row, third column, right? It takes all the pixels that are around it. Look at this, it takes all the pixels around it, right? Cool. Now it multiplies, again, I have a kernel here, right? The kernel is sort of fixed kernel. I do the Hadamard product. What is a Hadamard product? Look at this, I do this multiplication like this, element-wise multiplication. So 0 multiplied by 4, look at this. So 0 multiplied by 4 is 0. Again, 0 multiplied by 0 is 0, 0 multiplied by 0 is 0. So first row I have multiplied. Let's look at second row. 0 multiplied by 0 is 0. 1 multiplied by 0 is 0. 1 multiplied by 0 is 0. So I get second row also all zeros. Third row, 0 multiplied by 0 is 0. 1 multiplied by 0 is 0. 2 multiplied by minus 4 is minus 8. Right? So now I add up all these. Add up all this. So plus this, plus this. What does it return? It returns minus 8. Right? This minus 8 is present here. This is how I generate one pixel value in the output. Now, if I want to generate another pixel value, suppose if I want to generate, let's say, this pixel value. How do I generate this pixel value? I go to the corresponding pixel here. I draw a 3 cross 3 matrix around it. Look at this. This is my 3 cross 3 matrix. I'll do the Hadamard product. We just discussed, or element-wise product, right? We just discussed that right now, right? So I take this 3 cross 3 matrix. I do the element-wise product with my kernel and sum up all the values. And what I get here is my output, right? Again, the way this output is generated is we go from one pixel to another pixel. On every pixel, we try to put this kernel. So effectively, what are we doing? On every pixel, we are drawing this 3 cross 3 grid because my kernel is 3 cross 3. I'm multiplying element-wise with this convolution kernel and I'm generating an output. So this operation is called as convolution 2D, right? Again, remember, what is this based on? If you think logically, this is basically based on your element-wise product of matrices, because element-wise product, right? You can think of this as one matrix. You can think of this as another matrix, right? You're doing element-wise product and you're doing this for every pixel here to generate the output. Now you might say, what the heck are we learning? Why are we learning all this? This sounds too theoretical. I'll show you some simple application of this. Very simple application. Let's actually take an image. Okay, I've taken this example from SciPy. Okay, so I'm importing SciPy and SciPy miscellaneous. So SciPy has an image called as Ascent. I'm just loading an image. Look at what I'm doing here. I'm just loading an image here. Now, if you want to look at what is the data type of Ascent, okay, let's actually look at that, right? So print type Ascent. Yeah. Let's see. Okay. So so I'm just loading a ND array. Look at this. What am I loading here? I'm just loading an ND array. Okay. So there is actually an image which is already inbuilt in SciPy. I'm just loading that image. But what is that image? An image is nothing but it's a NumPy ND array. What is the shape of the ND array? 512 cross 512. So what do I have? I have an array which is of a two-dimensional array which is of size 512 cross 512. If I want to visualize this image, it's very, very easy using matplotlib, right? Again, we have discussed this in the course videos when we learn some image processing algorithms. It's actually one-line code. All I have to say here is import matplotlib as PLT. I just have to run this plt.imageShow. So imshow is a command that matplotlib borrowed from MATLAB. Actually, imshow, I actually used imshow. It's been there in MATLAB for many, many years, right? So matplotlib borrowed the same syntax from MATLAB. The imshow function is also there in MATLAB. So they just use the same thing because a lot of people who are using matplotlib used to use MATLAB earlier, right? MATLAB is a completely different tool. Okay, we don't have to worry about it. So what am I saying here? Again, you can read the documentation here. The first parameter has to be what is the image type? What is the image? What is the matrix that you want to show? ImShow basically means image show, right? And I want to say that the color map for this is grayscale. This is not a color image. This is a grayscale image. And I'm saying the minimum value is 0. The maximum value is 255. Again, this is very specific to image processing. That in each of my values, look at this. When I'm representing an image, right? So the value that is here rise between 0 to 255. 0 means full dark black, right? 255 means full white. That's what it means, right? So cool. So if I just do this, what do I get? I get an image like this. This is an image of a staircase that somebody is climbing onto, right? Very simple concept. So what I've done here, I've loaded an inbuilt image in SciPy as a 2D array. Now let's apply a very simple convolution operation. Okay. So first let me create a convolution kernel. Okay. Again, there are lots of convolution kernels that are available in machine learning and in image processing. In image processing and computer vision, there are like tons of kernels that are there. One of the simplest kernels is this. So what am I saying? I want to create a kernel like this. My kernel is basically NP1's KK and K is 10. Which means I'm creating a kernel which is of size 10 cross 10. My kernel is a 10 cross 10 matrix with all ones. With all ones. Then what am I doing? I'm saying how many ones are there here? There are 100 ones, right? Think about it. If matrix is all ones and there are 100 cells here, the sum is 100. Then I divide all of these values. Look at this. I divide all of these values. Kernel equals to kernel divided by NP sum kernel. So what happens to each value here? Each value becomes 0.01, right? So if I just print my kernel, I get this. It's a 10 cross 10 matrix. Look at this. It's a 10 cross 10 matrix with very small values here. Now I'll apply this kernel. Look, I can apply this very easily. Again, the signal is in, look at this, is in SciPy. SciPy has a way to build 2D convolutions. Again, they are also available in TensorFlow, Keras, etc. But let's use SciPy now. Okay, SciPy and NumPy are like siblings. So signal.convolve 2D, which means it's doing 2D convolution. And what do I want to do? I just want to do a 2D convolution between Ascent. Ascent was my image, right? And my kernel. What I get my output as blurred. Okay, so I'm just calling this output as blurred. Let me show you the image. What happens to this image? If you look at this image looks like a blurred version of this image, right? So the kernel that we create is called as a blurring kernel, right? If I just increase this size, if I just increase the kernel size and re-execute it, it will take a couple of minutes. Look at this, it is more blurred now. If I increase the size of the kernel, look at this, if I increase the size of the kernel, it becomes more and more blurred. So the operation of image blurring, look at this, the whole operation of image blurring the whole operation of image blurring can be represented as a simple 2D convolution operation. You can represent it as 2D convolution, and 2D convolution is nothing but it is simply element-wise matrix multiplication. It is element-wise matrix multiplication, also called as Hadamard product. It is element-wise matrix multiplication plus for loops, right? Because you have to do this for every element in the input image, right? So look at this. For every element in the input image, you have to do this element-wise product and then get the output value. So if you think intuitively, what is image blurring? Image blurring is simply 2D convolution. And what is 2D convolution mathematically? It is simply mathematical. If you think about it at its core, it's simply matrix multiplication with a bunch of for loops. So most of mathematics that you learn, most image processing algorithms, or at least a good number of them, if not all of them. Similarly, if I want all the edges in this image, which is called edge detectors, Again, there are kernels for edge detectors. There are a bunch of kernels called edge detectors. Again, you can just Google search for them, you get kernels for that, and you can try it. So, for example, let's say you do edge detector kernel. Edge detection kernel. Okay, let's go to, okay, there is something called Sobel Operator. Okay. Again, so look at this. If this is my input image, look at what Sobel Operator does. Okay. So if this is my input image, I can get my output image like this, where all the edges are highlighted. Look at this. I can do this using two kernels called as which are called as Sobel operators or Sobel kernels, which is named after Erwin Sobel and all these things, right? So edge detector is also nothing but convolution operation. There are a lot of operations. Actually, convolution is such a foundational concept of image processing that convolution is the core concept. It's the core concept behind most of deep learning on images. It is at least one of the most important concepts. Today, deep learning techniques on images are able to work because of the concept of convolution. If we did not have convolution, it would have been extremely hard to make it work. And convolution itself is nothing but matrix multiplication. Is nothing but matrix multiplication or Hadamard product and things like that, right? So a lot of complex concepts in machine learning, deep learning can be broken down to simple linear algebra. Again, in the interest of time, I cannot cover more examples here. So what I've done here is we will revisit these kernels again. We'll do some sessions on basics of computer vision and image processing, right? In these, again, we'll revisit the concepts of convolution. We'll learn many more convolution operators. We will learn OpenCV or foundation basics of OpenCV. OpenCV is a huge library for computer vision. We'll learn some of the basic operations in OpenCV in the context of machine learning and AI, right? So we'll do some sessions on these in the future. But if you want to read some nice examples, here is a very nice blog that I came across. Just look at it. I'll share this whole document. This document is image processing using Numpy. They have taken an image. Again, very simple, very easy to read code. They get RGB colors. Again, they do it on color images, right? So very nice. They do a lot of operations on this. It's a nice post. If you're interested to look at more operations on image processing and don't want to wait for that live session, here is a nice link for additional reading. Cool. So now again, the reason I put this concept in front of you is because I wanted to show you how powerful, simple matrices that you may think, hey, what the heck are we learning, right? Something that is as simple as this is extremely useful. Okay. Yeah, somebody says, finally, I have something to play with. Yes, you can play with this example. There are tons of links. Again, you can do it very easily. Okay, I know a lot of people love to play with image data. That's why I've shown this example. Okay, cool. Again, I'll try to add more and more image data in the future sessions also. I know it is very interesting for people to play with. I understand that. Okay, again, we have done in the previous sessions, we talked about circle, point in a circle, all that. I just wanted to extend that. Again, it's a very simple extension because spheres are sometimes used in machine learning, not as much as planes, but in some instances, we do use hyperspheres concept. Not as much as planes, to be honest. But I just wanted to quickly cover it because anyway, we have it in the course videos also. Okay, so what is a sphere? Sphere is a simple extension of circle to d-dimensional space, right? So you have circle in 2D, the similar shape is sphere in 3D, and hypersphere in high dimensional spaces, right? Again, since we can't draw high dimensional spaces, hey, I'll share this notebook with you at the end of the live session in the comment section itself. So please don't worry about it, right? I'll surely share it. Okay, cool. So a couple of very simple operations we'll learn, some very basics. These are commonsensical. So imagine if I have a circle, I can't draw a hypersphere. So let's look at this. Suppose if I have a hypersphere like this with center and radius, of course, the center can be represented using a d-dimensional vector, because the center is, because let's assume this is d-dimensional space, right? If this is d-dimensional space, I can represent the center as a d-dimensional vector like this. R is also a d-dimensional vector. The radius is also a d-dimensional vector, right? Because it says in each dimension, what is the radius of this circle, right? So that's important, okay? Cool. Actually, you can think of radius, you don't have to think about it like this, because for a sphere, okay, sorry. So you can think of radius as just one number. Radius is a float, I'm sorry. So radius is simply a float value if you think about it logically, right? So because your circle is fixed in all dimensions. So basically what is a sphere? Sphere basically says all the points which are at a distance r from here is within my sphere, right? So r is not a vector, r is a float, right? Simple. And how do you do some simple operations on this? It's very simple. So I think I did a mistake here. Okay, let me just say r equals to 10. I did a small mistake here because again, the radius, let's just think about it. Just give me a second. I hope I have not made a mistake. I was in a hurry when writing notes for this because I was running out of time. So the center obviously belongs to RD. My radius has to be a single scalar value, right? Because what it means is, given this circle, all the points which are there in this radius in all directions, yes, r is a scalar, r is not a vector. I'll write the code, I'll modify the code as we go. Okay, so a couple of operations that we wanted to read. No, so how do you represent a circle? Very simple. You represent the center using a vector, radius using a scalar, and a circle is basically a tuple of the center circle. So I use C for center, R for radius. Very simple. Right, so I don't have to compute linear algebra, norm, R, all of that stuff. I don't have to worry about this. Okay, so some very simple stuff. You can represent a circle very easily using the circle center and radius. Nothing very fancy. Now, if you want to find if a point is inside a circle or outside a circle, how do you do that? Next, very simple question, right? If you think about it logically, how do you do it? How do you decide whether a point is in a circle or outside a circle? It's a very simple concept, right? So you just compute. So given a point like this x, right, you want to say whether this point x is inside a circle or outside a circle. That's an important operator, just like for planes, right? You have positive, suppose if my w is in this direction, if this is my plane, I have positive half space and negative half space. So a plane literally divides the space into two parts. Similarly, a sphere divides the space into inside the sphere and outside the sphere. It divides the space into two parts. And that's what is useful in some machine learning algorithms. Not all, it's seldom used, but I wanted to introduce the concept so that even if you read a research paper in the future, you can understand it. So what is the distance of a point x? So there are two things, right? So how do you determine whether a point x is inside the circle or outside the circle? Very simple. If this is my point x, compute the distance from x to c. Just compute the distance. If the distance is less than r, it is inside. Very simple. We have seen this for circle earlier, right, in the previous live sessions. If d equals to r, it is on. If d is greater than r, it is outside. Very simple. Nothing fancy, right? Very simple. So we can easily write the code for it, right? So imagine if I have a point like this. Okay, so I'm creating a point x1, right? I'm just creating a point x1. And what am I saying? It is center plus zeros, which means x1 is same as center. Right now, how do I compute the distance? Suppose if this is my circle, if this is my point C, if this is my point x1, how do I compute it? The distance is nothing but do x1 minus c. If you do x1 minus c, what do you get? You get this. And if you take the norm of x1 minus c, norm 2, what do you get? You get the distance between these. Right? Just simple vector algebra. Look at this. If you have vector like this, if you have vector like this, v1, v2, right? If you compute v1 minus v2, right? And if you take v1 minus v2 norm 2, what do you get? You get this distance. You get this distance, right? That's what V1 minus V2 gives you, right? Similarly, same concept here. C is represented by a vector C, x1 is represented by a vector x1. If you want the distance between both of them, it's very simple. Take the norm of x1 minus C. Very simple, right? So what is my x1 here? My x1 is C plus zeros, which means my x1 here is C. So I'm computing the distance of C to itself. Just a test case. It should give me 0, right? Yes, it gives me 0. On the other hand, let me create one more. So imagine if I create my x2, another point x2, right? How do I create my point x2? I create my point x2 as the center plus all the radius values. That I have. Center plus the radius value that I have. Okay, let me just execute it once. Does this lead to an error? Because it doesn't lead. Okay, cool. So, or else let's just, okay, so that's okay. Center plus radius, let's just change this. It's okay. So, if I do this point is, I'm taking the center, I'm adding radius, which means I'm adding, so if this is my sphere, I'm saying add r on all the dimensions and then add some more value to this. Obviously, if I add r to each of the dimensions, this point x1 has to be outside. Obviously, it has to be outside, right? It has to be outside, by design, right? So now if I do x2 minus c, look at this, or this point I'm calling it x2, right? So if I do x2 minus c, and if I take the norm of it, norm of x2 minus c will give me this distance, right? Norm of x2 minus c will give me this distance. Now if this distance is greater than r, look at this, how do you determine whether you're inside or outside? My r here is 10. Okay, if the distance is, as we've just seen a while ago, again, very simple, this, whatever you learned with circles, same concepts hold here also. When the dimensions become very large, there are other problems that we discuss when we handle high dimensional data, right? You get something called as cursive dimensionality and others that we'll learn later. For now, as long as the dimensions are not too large, this logic certainly works well. Now, how do you find the distance? Okay, this is an interesting thing, right? How do you find the distance from a point to a hypersphere? Suppose you are given a hypersphere with center r and radius, center c and radius r. You want to find the distance from point x to the shortest distance. You want to find the shortest distance to the surface of the sphere. To the surface of the sphere. So if this distance is d, how do you find this distance d? How do you find this distance d? Again, please understand that this is in d-dimensional space. This is not in 2D. Okay, again, I'm only talking about d-dimensional space because it's easier to generalize. The whole objective of learning linear algebra is to operate in high-dimensional spaces and to operate on data matrices, right? So how do you find this? Okay, this is a good question. Can anybody help me with this? What is this distance? So I want the shortest distance. Between a point x and a circle represented with c and r. Okay, let's assume this is how I represent a circle. I represent a circle with the center and radius r. If I want this, how do I compute this? Can anybody help me with this? I'm looking at the comment section. So if somebody can help me with this. Yeah, very simple. I'm glad you guys got it like in no time, right? You just compute the distance between. So this is very simple. This is basically the distance between center and x. What is the distance between center and x? It is nothing but this. This is basically this distance. This is basically this whole distance. From this distance, we know that this distance is radius. You subtract r. From this, subtract r. You get this remaining distance. That's it. It's just literally this. Like one line code. Again, this is sometimes used in machine learning. That's why, or I should say in clustering algorithms and things like that, this is sometimes used. Okay, so let me just show you that. Suppose if I take a point like this, cool. So, okay, I don't have to do this. I just have to say minus r. Okay, linear algebra, norm x2 minus r. Yeah, so this will work. Okay, so what do I get? This is my distance. So I'm just creating a point here, right? I'm saying the distance between the point to the circle. How do I get the distance? It is basically x2 minus c or c minus x2 norm minus radius. Done. Problem solved. Again, what we're doing right now is just a surface touch of linear algebra. Let me tell you other topics in linear algebra and how they're extremely powerful. Okay, again, this list is not exhaustive. This is just some of the topics. Okay, again, we'll try to cover these in the future sessions. In the next sessions, there is data matrix, operations on data matrices like normalization and standardization. Again, you can watch some of these free videos of our course that are readily available. So you can just go to AppliedAICourse. You can just go to AppliedAICourse, go to view course. Some of these videos are freely available, so please feel free to check it out. Look at this, dimensionality reduction and visualization. All these videos are available. You can learn about the basic operations. You can also learn about principal component analysis. Again, we go into the mathematical depth with some code examples, etc. There is also T-distributed stochastic neighborhood embedding. Again, this you cannot call it pure linear algebra method because it's more based on other concepts, like it's based on optimization, etc. But we thought since we covered PCA, we thought we'll cover TSNE also. So TSNE is not a pure linear algebraic method. Okay. While dimensional reduction is a concept in linear algebra for sure. So some of the free videos are available, so please go check it out if you're interested. So these are some of the concepts for sure, right? So we'll do a few sessions on these topics next. Then if you look at linear regression, if you pick up any major book on linear algebra, they cover linear regression, right? Again, we covered linear regression after logistic regression in our course. You can pose most of linear regression as, again, linear regression can be studied from three fronts. There are three ways to study linear regression. You can read it from a pure linear algebraic perspective. You can read it from a pure probability and statistics perspective. You can look at it from an optimization standpoint. There are three ways of looking at it. Okay, so we focused more on the optimization way of looking at it and linear algebra way of looking at it. We also gave hints about probability and statistics way of looking at this concept in the course videos, but we didn't go too deep into it. Okay, then you have this whole concept called as linear programming. Again, we'll do a live session on linear programming when we come to optimization methods. Then you have this singular value decomposition, matrix factorization. All these concepts are extremely useful in the area of recommender systems. Again, these are useful in data visualization. If you want to visualize 100-dimensional data, how do you visualize it? Right, so a lot of linear algebraic techniques like principal component analysis, dimensionality reduction, TSNE are used in that context. Again, those of you who are interested in more undergraduate level, because I believe some of, so let's look at this. So we have done one more course. Let me open this here. We have done this for GATE computer science students. Okay, so you can just go to this. So I'll share this link with you where these videos of linear algebra are freely available. So this is more of an undergraduate level, not necessarily computer science. So whether you're a CS student, right, whether you're a CS or any engineering student, ECE, mechanical, name it, any of these engineering students who want to learn linear algebra from a more undergraduate syllabus perspective, we have a bunch of videos here. Again, I try to explain all of this from the geometric intuition perspective, right? Whichever videos I do for any subject, I try to do it from a geometric intuition and practical application perspective. So the videos here are more like your undergraduate syllabus. So we learn about vectors, linear transformations, determinant of a matrix, why do we need all these, right? Again, rank of a matrix, solving linear system of equations, decompositions. Again, this is done more from a undergraduate perspective. So if you're interested, these videos are also freely available. Please go check it out. And if you think somebody will benefit from that, please share it with them, right? So, okay. So that's all I had for today's session. So I hope, again, let me just share this with all of you. Anyway, since we are at it, anyway, I'll share this with all of you, right? So please give me a few minutes. After this live session, I'll share it with you. So any questions related to this? Oh yeah, so as somebody said, you should have shared 3 blue, 1 brown. Yes, so that's a good point. I forgot to mention that. 3 blue, 1 brown linear algebra is also very good. I'm happy you mentioned this, right? So 3 blue, 1 brown is a phenomenal channel which talks about linear algebra videos. Again, all the linear algebra that you learn there may not be applied in machine learning and AI. Please don't forget that, right? Again, we have also referred to 3 blue, 1 brown in these videos. As somebody says, you should have done it. So don't worry. Even in our linear algebra videos here, we do refer to multiple textbooks. We do refer to multiple external resources. So we try to always point to good resources, not just our own. I hope you understand that. So somebody says, please do more live sessions more frequently. Again, we are trying to do live sessions mostly whenever the topic is basic that anybody external to the course also can understand, right? So if it requires students to go through our videos extensively, have done our assignments, then we are not doing it externally because people may not benefit from it much, right? So that's how we decide whether a live session should be public or private. Cool. Somebody says, what is a good book for probability and stats? Oh, there's a very nice book. Again, there are multiple good textbooks for it. One of the best textbooks that I know of is Think Stats from an applicative perspective. I like this book a lot because I think this book is also publicly available. Yes, you can. It's available to download in PDF. This is a slightly old book, but Think Stats is a very good book because they try to teach the concepts by using a real world data set. So they take data set from National Institute of Health. They take an actual data set and they try to introduce concepts from the practical perspective. It's one of the best books from a practical standpoint. There are a lot of good theory books, but for a machine learning, you have to know how to apply things. So Think Stats is one of my favorite books. So when will we discuss SVD? We'll discuss it when we do live sessions on recommender systems. Do you have to learn deep in linear algebra for machine learning AI? Again, what is depth? That's my question, right? So what do you define as depth? I've listed all the concepts here, right? I've listed most of the concepts, if not all the concepts. So for machine learning, at various points, you need various concepts. The concepts that I just discussed right now are the foundations, but you need to know a lot of other concepts. These are all the concepts that you need to know if you really want to become a good machine learning engineer in linear algebra. Again, this is not all that is there in linear algebra. There are many other concepts in linear algebra, but these are certainly what you need to know for machine learning. You can think of it as a good set of concepts. Cool. How do we determine the W vector? Oh, so you're saying, okay, so good point. So we determine, so let me try to answer that question briefly. So in linear regression or logistic regression or SVM, we try to find a hyperplane that separates positive points from negative points. Again, those of you who understand it can understand it perfectly, but we try to find this hyperplane. If you have a hyperplane basically has two parameters, right? W and B. So this is my W and I have a B corresponding to it. We try to find this hyperplane by solving a mathematical optimization problem. Look at it. We have done a few live sessions earlier, right? Where we talked about maxima and minima, right? Again, these are concepts that you may have learned in your undergraduate level computer science. That you may have learned at 11th and 12th class mathematics, not even undergraduate level computer science, right? So optimization is basically a simple extension to concepts of maxima and minima that you learn in your 11th and 12th class. If you recall, we have actually discussed this in the previous live sessions in our numerical, again, all of them are available on YouTube. This is called numerical programming. Okay, so we have done 2 sessions, numerical programming 1 and 2. So we've actually solved some problems using maxima minima. The same concepts are used, but certainly at a next level when you want to find W, right? So that's how it's actually solved in the real world. So could you please share similar list of topics for probability and stats? Again, if you want a good list of topics, the textbook is certainly a good starting point. Again, if you want a list of topics, you can always go to our website. You'll find the list of topics that we think are very relevant, right? So you can just go to probability and stats. These are all the concepts that we think are very important for somebody who is picking up machine learning and deep learning. This is a good, again, this is just a subset of topics. You can always go here, you'll find a list of topics. Topics is easy. Again, but please remember that no topics list is static. Things change, right? So you have to evolve with it. Again, it's almost impossible to do depth first. As I've just mentioned a while ago, please don't learn depth first. Please learn breadth first. Learn little bit of linear algebra that you need. Learn little bit of programming, little bit of data structures and algorithms that you need, little bit of probability and stats that you need, little bit of optimization that you need, little bit of machine learning techniques, little bit of clustering techniques, little bit of deep learning techniques first. After you learn all these basics, then you can say, okay, I want to go deep into linear algebra, or I want to go deep into programming, or I want to go deep into probability and stats. This is what we recommend. Because when you learn the breadth of concepts, you can start transitioning to machine learning and data science careers. There is no limit to how much you can learn. As I told you, like I've been reading research papers for the last 12 to 13 years. And there is no end to it. It's almost impossible to keep track of all the advances. Let's take a very simple area, right? Probability and stats. There is so much of great innovation that's happening in probability and statistics that it's impossible for any single person to keep track of everything. right? But I try to do my best to go deeper into each topic whenever I get some time. Okay, first breadth is important, then depth. If you do depth first, you might become an expert in linear algebra, or you might become an expert in programming, but you'll never have the breadth of expertise to become a data science or a machine learning guy. So somebody says how to compute eigenvalues and eigenvectors. Again, it's simply a simple function in Numpy. Again, that is something that we thought we'll discuss when we learn principal component analysis, because it requires eigenvalues and eigenvectors. Again, if you want to know that, right, it's actually just Numpy eigenvalues. Just Google search. Okay. So in Numpy linear algebra, there is something called EIG. Read up the documentation. Okay. What does it want? EIG A. A is basically matrices for which eigenvalues and eigenvectors will be computed. What does it return? It returns W and V. Okay, it returns eigenvalues, it returns normalized eigenvectors. That's it. There is sample code here. Like it took, like, even if you don't remember it, it takes 30 seconds to figure it out. Right? So it's actually fairly easy. So somebody is saying radius should be a vector. Why should it be a vector? I thought it should be a scalar, right? So I also got confused with that when I was writing the notes. So imagine if this is my sphere. Okay, think of a sphere, right? Sphere. Okay, again, I couldn't draw a sphere here. Sphere on x-axis, on y-axis, and also on the z-axis. The radius is the same, right? Because if I change, so let's take a circle, right? Let's take a simple circle. The circle, right? Circle is 2D, right? Right? This is my x-axis, and let's say this is my y-axis. Let's just say, right? So my radius, so my radius on the x-axis is the same as the radius on the y-axis. There are no two different radius. So in 2D space, I have only one radius. Now, if there are two different radii, right? If this is different from this, what do I get? What I get is not a circle. What I get is an ellipse. Think about it, right? So imagine, okay, let me change the diagram here. Imagine if I have this, right? If this is different from this, what I get here is actually an ellipse and not a sphere. So for a sphere, the radius should be the same. Actually, I think I messed up because I was also thinking of hyperspheres in my head. Hyperspheres have a different way of encoding it, and we don't use hyperspheres much in machine learning. That's why I did not cover it. Sorry, hyperellipses. Sorry, these are hyperellipses, not spheres, right? Even hyperspheres, they're very few times used. I don't use them regularly, to be honest with you. I don't use techniques which use hyperspheres regularly, but there are one or two odd data mining techniques which use it, right? That's why I thought I'll cover it. Again, what topics are required? As I just mentioned, all these topics are required for sure for top product based companies. No doubt, hands down. So please mention the topic which you should be ready with matrix algebra to get matrix factorization concept. Again, don't worry about it. Matrix factorization is just about matrix multiplications. If you know how to multiply two matrices, you have the basic knowledge for matrix factorization, right? Again, matrix factorization and NMF are solved using optimization techniques. Cool. I think, Swapnil, I just mentioned this, right? I think this is a good starting point. Again, most of the questions that I remember from the interviews are mostly revolve around these. Of course, there are real world problems asked to you, and people ask you, okay, how do you do matrix factorization when the data has this problem, right? Or how do you do, let's say, for example, take linear regression, right? Linear regression can be understood from a linear algebraic perspective. What if your data has outliers? What happens to your linear regression based model, right? Or how does singular value decomposition or PCA behave if there is noise in your data? How does it work, right? These are actual questions that I have asked in interviews, right? If you take non-negative matrix factorization, what happens to how do you do non-negative matrix factorization when the data is very large? Again, people may not ask you just the mathematics. People ask you, again, to answer some of these questions. For example, what happens to outliers? To answer this question, you have to know the mathematics and you have to be able to apply the mathematics in the context that there are outliers, right? How does NMF work if there is a large amount of data? To understand this, you have to know the NMF mathematics internally. So a lot of questions are not like, okay, explain me the optimization problem for NMF. That's a joke, right? Or the more real product-based company questions are, okay, in NMF, why do we have regularization? Again, regularization is another concept which we learn in optimization, which is also sometimes covered in the linear algebra courses, right? So again, lot of things that are there in machine learning can be seen from a linear algebraic lens. Oh, this Cinderella man, I know this guy. Okay, so you're asking me about beginner projects to become good in Python, right? So that's very simple. I've mentioned this multiple times, right? Pick up, just instead of doing full projects, write code. I think I mentioned this in the previous sessions also, right? There are these 101 practice sessions, 101 practice questions in Numpy. I think I mentioned this. Okay. Just Google search practice questions in Numpy, practice questions in Pandas. Instead of doing full-fledged projects, try to get the breadth of experience first. Then you can do projects, right? Because the projects that you can do with basic Python are fairly limited. Okay, there is one live session that we have done that could help you if you want to do projects, right? So let me show you. Let me just go. I'm just thinking AppliedAICourse web API. Okay, so here is a live session that we have done using web APIs in Python for machine learning. Again, you can use a lot of web APIs and build some simple machine learning solutions. So this live session, again, this is publicly available on YouTube. You can go check it out. Again, you can use web APIs from Google, Azure, all these guys. And again, all you need is basic. So Google, Azure, right? They give you a lot of nice machine learning functionality with just an API call. So if you want to become better at Python, also you should practice problems without doubt. But if you want to do a simple project, you can use these web APIs and build a simple thing. You can build a simple face recognition system, right? You can do a simple speech to text or do a simple chatbot. Again, we have a live session on how to build a chatbot also. I think it's also on YouTube. We've done it more than a year ago, right? So there are some of these live sessions that are publicly available that you can check it out. Again, if you want to check out all of our live sessions in one place, we have put it in one place. We just did that recently because it's hard to maintain everything. So if you just go to live sessions link here, so all of our public live sessions, there are all these public live sessions. All of our public live sessions are accessible here, right? So you can just go here. So how to build this, high level design, right? So web APIs, how to build a simple YouTube recommendation using basic mathematics, the live sessions that we have done recently, right? There are some live sessions earlier. So my suggestion here is there are a bunch of live sessions that are publicly available from which you can build a simple project if you choose to. How to search for a research paper? That's a very good question. So the way I do it is this. So I think many people don't know this. Go to scholar.google.com. Scholar.google.com. Google Scholar is the best tool that I know of for research, right? So again, this only gives you research papers. For example, if I want a research paper on BERT, okay, I just search BERT. Okay, so I can filter it. Okay, so BERT, okay, it's giving me multiple papers. So if I say from 2016, it gives me all the papers. Again, this gives from the whole of science, not necessarily deep learning, machine learning, etc. So deep learning. Okay, so this is whole of science. BERT deep learning from 2016. I get a bunch of papers. But why am I getting large batch optimization? BERT transformer. I think the keywords are messed up. Okay, so yes, this is the paper. Again, whenever you are picking a paper to read, it's very important that you pick papers with lot of citations. The citations tell how important this work is. Remember, this paper was published in 2018 and this already has 4,531 public citations. What is a citation? I write a research paper and I refer to this research paper. I say, okay, BERT, which is discussed in this paper. So if I cite this paper, I get a citation. So there are 4,531 other research papers that refer to this research paper. That's how important this research paper is, right? So you should always look at citations. If there are not enough citations, maybe it's not such an important paper, to be honest with you. Again, citations can also be biased. There is some problem with citations. But if I want papers from 2019, let's look it up. Okay, I can also sort by date, sort by relevance. There are multiple sort options, right? So my suggestion always is to use Google Scholar. Again, You need not always use Google Scholar. If you just go to Google and search this, it also says, look at this, it also says this at the top. It says scholarly articles of BERT transformer. It tells this also, right? And it says, okay, this is the top paper. It is cited by 4,531. So what I do is I directly search on Google. I get some papers here. If this has high citations, I go to Google Scholar and search. Okay. Otherwise, you don't get blogs and all that in Google Scholar. So, right. So the second place is there are tons of nice blogs on BERT. So whenever you're reading a complex research paper, if there are other blogs which explain the research paper, I recommend that you first read these blogs, because reading a research paper is written for other researchers to understand. And if you're already not at the research level, probably it's best to read others' blogs, because you can easily understand this. This is written for more students, not at cutting edge researchers. Once you understand the basics, then you can read the research paper, because research papers are actually written for researchers very often. So don't try to understand the research paper in the first go. Again, if you have spent years together doing it, you will understand it. But otherwise, when I was a student reading my first research papers, I would read blogs if somebody has written them. That's a good starting point, and then go and read the research paper at the end. That's what I would recommend. Cool. Okay, folks, sounds very good. Thank you very much. And what we'll do is I'll post this collab notebook in the comment section, and I'll also post it in the description section of the video. Okay, thank you very much for joining in. See you again. Bye bye.